In this video, I am going to solve some of the previous year questions from nuclear physics. So these will be helpful for the preparation of KSET exam as well as for NET and GATE exam, because the syllabus for these competitive exam is same. So if you are new to my channel, please subscribe my channel for upcoming videos. Let us solve the questions here. The first question is the cross section of the reactions. They have given two reactions here at a given energy are same due to which of the parameter is going to be conserved: baryon number, charge, time reversal, or parity in the given four options. If you carefully observe the two reactions, first reaction involves the proton plus pion minus. After reaction, the sigma minus hyperon and the kaon plus we will get. So if you observe the second reaction, the particles involved are the same as in the first reaction, but they are antiparticle. So the answer for this question we can have here, the charge conjugation happens here. The particle involved are proton, pion, sigma hyperon and kaon. And here are the antiparticles, these all. Okay. So then charge is going to be conserved. That's why the option C is correct here, charge conjugation. Second question, which of the following function describe the nature of the interaction potential V of R between the quarks inside a nucleon? R is the distance between the quarks and A and B positive constants. They have given here the nature of the interaction potential as V of R. Okay, in four options we observe the V of R, and R is the distance between the quarks A and B. A and B are what the quarks here in all the four options. If you say R is the distance between them, then which option is correct here? So if we go for the theory of the interaction potential, it involves the two terms here, negative minus A by R plus B R. So then option B is correct. V of R, interaction potential, which is equal to A is the quark and B is also quark, which are separated by distance R. So minus A by R plus B R is the correct answer, interaction potential. Which of the following reactions violates lepton number conservation? So leptons are example for fermions which have spin half, all the fermions. So leptons, if we take examples are proton, electron, neutrino, antineutrino. So if you observe all the four reactions involves the leptons. If we go for the equation 1, here the electron and the positron after reaction give neutrino and antineutrino. The charge, if you observe here, -1 plus 1. Before reaction, after reaction, 1 minus 1. So it is allowed. So the second reaction, if you go in the given option, electron plus proton, after reaction neutrino plus neutron. So here also charge is conserved. So for third reaction, if we go electron positron, that is E plus, and neutron, after reaction will give proton and neutrino. So this is not allowed here. Actually this is E minus. So here the charge conjugation will not take place. If we go for this is actually not valid, fourth option. So option C is correct here, which is violated the lepton numbers. Fourth question, the baryon number of proton, the lepton number of proton, the baryon number of electron and the lepton number of electron are respectively. So for the given question, we have the standard values of baryon number for proton is 1 and lepton number of electron is 1. So from the given question, baryon number of proton is 1, lepton number of proton is 0, baryon number of electron is 0 and lepton number of electron is 1. So option, if we carefully observe, 1 0 0 1. So option C is correct. Typical energies released in nuclear fission and nuclear fusion reaction are respectively. So always fission reaction, the amount of energy released is 200 mega electron volt and in fusion 10 mega electron volt. So then option D is correct here. Nuclear forces are spin dependent, have non-central part, spin dependent, have a non-central part, spin dependent, have no non-central part, spin independent, have a non-central part. So actually the nuclear force is always spin dependent and it is a non-central component of the force. Then option B is correct. Nuclear spins of carbon 14, magnesium 25 nuclear respectively. So carbon 14 has 6 proton and 8 neutrons. Magnesium 25 has 12 proton and 13 neutrons. So carbon is even nuclei and magnesium is even odd nuclei. Then option A is correct. 0 for carbon 14 and half integral for magnesium 25. Question 8. Asymmetry terms in which Sacker semi-empirical mass formula is because of non-spherical shape of nucleus, non-zero spin of nucleus, unequal number of proton-neutron inside the nucleus, odd number of protons inside the nucleus. So semi-empirical mass formula asymmetric term is given by always asymmetry means not equal. So here unequal number of protons and neutrons inside the nucleus. The spin and parity of beryllium-9 nucleus are predicted by the shell model are respectively. So according to shell model, we have to write the equation for beryllium-9 here. So for the eighth question, the unequal number of proton neutron, here the semi-empirical mass formula involves 5 terms. Among them, the asymmetric term is involves unequal number of proton neutrons. So option per term, the second term is for asymmetry, unequal number of protons neutrons. So A minus 2Z is equal to 0, which is not equal. So the question 9 here we should predict according to shell model. Beryllium has 4 proton, 5 neutrons. Even nucleon doesn't contribute to spin. Okay, then 4 proton are not going to contribute. 5 neutrons will have the in terms of sp df. If we write s here, only 5 neutrons are there, so we require s orbital and p orbital. So 1 s1 by 2 to the power 2 and 3p 3 by 2 to the power 3. So last nucleon is in the p orbital, p 3 by 2 state. So spin is how much here for p orbital? 3 by 2. So parity is given by minus 1 to the power L. L is what? Angular momentum. L is equal to 1. for the p orbital. So here parity is -1. So spin is 3/2 and parity is odd. Option A is correct. The nucleus of an atom beryllium-9 consists of how many up quarks and down quarks? So again here the beryllium, as we know, 4 protons, 4 electrons, 5 neutrons. Okay. So 4 protons, if we consider, it is denoted with 2 up quarks and down quarks, proton, according to quark model. Then 4 into this 2 up quarks into down quark we can write, and it involves 5 neutrons. So neutron is denoted by 1 up quark and 2 down quark according to quark model. Then 5 into this value. Then if we multiply individual up quark and down quark, and if we add, so total up quarks will be 13 up quark and 14 down quark. Here 2 up quarks are there. So 4 plus 4, 8 up quark. Here 5 up quarks is how much? 13 up quark. So similarly here for down quark. Option B is correct here. 13 up quarks and 14 down quarks. Which of one of the following nuclear reaction is possible? So if we observe, all the nuclear reactions involve the nitrogen after reaction, which will give carbon and the beta particle along with neutrino. So if we verify all the 4 equations here, the equation, this equation is given here. Lepton number of beta particle is -1 and the neutrino is +1. So sum of lepton numbers will be 0 on LHS or RHS side. On left side, lepton number is always 0 because nitrogen is there. So option here, lepton number is conserved. So option A is correct, and remaining option, lepton number, is not conserved. So if we take the question, for the question, the option A is correct, where lepton number is conserved in this equation. For all other 3 options, the lepton number is not conserved. So option A is correct. Suppose that a neutron at rest in free space decays into proton and an electron. This process would violate. So for the given question, there is a reason behind that. In the nucleus reason, nuclear forces has non-central part according to the properties of the nuclear forces. So conservation of angular momentum is not as applicable in the nuclear reason. So but in free space, this reaction would violate conservation of angular momentum. So option for the question 12 is D here. A stationary particle in free space is observed to spontaneously decay into 2 photons, and this implies that photons have integer spin. Then photon is an example for boson, which have integral spin. So option C is correct here. Particle is a boson. 2 photons as we have. The masses of a hydrogen atom, neutrino and uranium-238 are given here. These are the masses of these 3 respectively. The binding energy of uranium-238 is therefore approximately equal to 1 atomic mass unit. They have given how much here? 931.64. So given data, with the help of that you can solve here. The Given fuel is uranium-238, which consists of 92 proton, 92 electron, 146 neutrons. So if we multiply with the masses of these three, we will get here, and we should multiply with the atomic unit also, the given value 931.64 mega electron. Then here if we add up, we will get 1580 mega electron volt, which is near to 1600 mega electron volt. So option C is near to that. So in the next question, an atom bomb consists of uranium-235 explodes and release an energy of 10 to the power 14 joule. It is known that each uranium which undergoes fission release 3 neutrons and about 200 mega electron volt of energy. Further, only 20% of uranium-235 atoms in the bomb undergo fission. So we can solve this for both the questions given data. The total number of neutrons released is about. So first you should note down the given data and then solve both the question. These questions will be repeated in GATE exam. Okay. So here the effective number of uranium-235 fissioned, that is equal to the ratio of 10 to the power 14 divided by 200 mega electron volt into the charge of electron, 1.6 into 10 to the power minus 19 coulomb. Then we will get the effective number of uranium fissioned, about 3.125 into 10 to the power 24. For each fissioned uranium 235, 3 neutrons are released. So number of neutrons released is, you have to multiply the value into 3. Then you will get 9.3 into 10 to the power 24. So the option B is correct for this question. Next question, the mass of uranium-235 in the bomb is about. So how much mass of uranium-235 is there? So number of moles of neutrons released is, with the help of the answer of the previous question, you should divide it by 6 into 10 to the power 23. So number of moles of uranium-235 attacked and multiply with 3 neutrons in the denominator. So you will get finally and the 20% they have given here. Further, only 20% of uranium atoms in the bomb undergo fission. So you have to multiply 20%, 100 by 20. Then you will get here the final mass of uranium-235 in the atom bomb, 6.1 kg. Option C is correct. Volume of a nucleus in an atom is proportional to the. So always the volume dependent on mass. So liquid drop model propose that density is constant. That means volume is directly proportional to mass. Option A is correct here. As one moves along the line of stability from iron to uranium nucleus, the nuclear binding energy per particle decreases from 8.8 to 7.6. This trend is mainly due to which is causing this decrease in the value of binding energy. Short range nature of nuclear force, long range nature of Coulomb forces, tensor nature of nuclear force, spin dependency of nuclear force. According to liquid drop model, suggests that long range nature of Coulomb force is responsible for discriminant in binding energy of higher masses. So that's why there is a decrease in the binding energy from iron to uranium that is 8.8 to 7.6. So option, that is the reason for due to the long range nature of Coulomb forces. Option B is correct. So this is how you can solve the questions related to uh, the nuclear physics. So like that you should try to solve the previous year questions from GATE or the KSET exam. Then you are able to solve the exam in the questions. So I hope these questions or this explanation will be helpful for you for the preparation of the upcoming exams, KSET as well as GATE exam. So also NET exam will be helpful. So thank you for watching, and please do subscribe my channel. If you want to have more information, you can go to the playlist. You will get the all details for the exam preparation. Thank you.